Hello, students. Here's the lecture for Module 8, Lesson 3, Tests on Contingency Tables. We'll talk about the chi-square test. We will also discuss Fisher's exact test. But let me take you back to Module 7, Lesson 4. This is when we saw hypothesis tests for population proportions. We learned about the z-test and the binomial test. Just to recall, the binomial test, this was an exact test. And the z-test was an asymptotic test. In this lesson 4 of module 7, we tested if the proportion of a certain type A in the population equals P0. Our null hypothesis was that the proportion equals P0, whereas the alternative, at least two-sided, was that the proportion is not equal to P0. Here, pi was the proportion belonging to type A. Here we had two categories. One was A, while the other was everything else, which you can think about as being not A. Now, we can write the probabilities underneath. A has probability pi, that was the proportion belonging to type A. Not A would have probability 1 minus pi, like this. More generally, we can have M categories. Here I think about as M being bigger than 2. We will discuss the chi-square test here, but let pi 1 through pi m denote probabilities for M categories in the population. The null hypothesis is that this vector, pi 1 through pi m, equals some specific vector of probabilities, p1 through pm, versus the alternative that this vector, pi 1 through pi m, is not equal to this specific vector. Here, p1 through pm are, well, they have to be non-negative because they're probabilities, and then the sum of all of the pi's must equal 1. How can we test this null versus this alternative hypothesis? Well, we use a random sample of size n from the population. And for each category, we can calculate the observed frequency. This comes from the sample. And then we can calculate the expected frequency for category I. This would just be n, the total number of our random sample, times this probability p sub I. This is the expected frequency under the null hypothesis. Now, the test statistic here for the chi-square test, we add up for all M categories. Here we take the square of the difference between the observed and the expected, and then it's normalized by the expected number. That is this Q. I've also just written it in words here. We take observed minus expected squared, and then, as I mentioned, normalized by the expected. We add up over the categories. You notice that Q is non-negative because we have this square in the numerator. Moreover, the test statistic is small when the null hypothesis is true. Okay, so under the null hypothesis, this test statistic asymptotically is distributed as a chi-square random variable with m minus 1 degrees of freedom. We calculate the p-value by taking the probability that this chi-square random variable m minus 1 degree of freedom is greater than or equal to this test statistic Q. And as usual with hypothesis testing, we reject H0 when our p-value is less than some significance level alpha. Some notes: the chi-square test is an asymptotic test. We can see that here. Moreover, the approximation is typically good when all EI are greater than or equal to 5. This says all expected frequencies are at least 5. That is the statement in words. Now, the z-test from module 7 is a special case of the chi-square test with m equals 2 categories. In fact, before I move forward in our notes and our lecture, let me go to our Canvas page from Module 7. What we're looking at is one of our Canvas pages. We have an example using the z-test. Now, here you can see is where I call prop.test, which is our z-test. Then the output of R, you notice it gives a chi-square test statistic. And I make a remark about this in our Canvas page below. So from probability theory, if you have a standard normal random variable and you take the square of it, that is distributed as a chi-square random variable with 1 degree of freedom. So the z-test, which we learned in the last module, really is a special case of the chi-square test. Well, in R, here's what we use for the chi-square test. Now, if you remember the name of this lesson, it was tests on contingency tables. So far, we haven't even talked about what is a contingency table, and so this is coming next. Let's consider a rectangular array having R rows for categories of X and C columns for categories of Y. The cells of the table correspond to all possible R times C outcomes. So when the cells have frequencies or counts of the outcomes for a random sample, this R by C array, or this is rows by columns, is called a contingency table. Okay, so in particular contingency tables, the values inside the tables must be non-negative integers. Well, in this lesson, we're going to talk about 2x2 contingency tables. This means the first variable has 2 outcomes, say A1 and A2. The second variable has 2 outcomes, say B1 and B2. So suppose we have the following observed frequencies for a random sample of size n. This part is the frequencies. You notice looking at this here, A1, A2, there are the 2 outcomes for the first variable, B1, B2, the 2 outcomes for the second variable, and then inside here are the counts or the frequencies for a random sample. So there are some relationships here, just to point this out, because we see letters and not numbers. But when we add this way, we get this total. So this says, for example, O11 plus O12 equals this R1. Similarly, O21 plus O22 equals this R2. I hope I'm making myself clear. Now, if you add this way, here are the totals. Okay, O11 plus O21 is this C1, O12 plus O22 equals C2. And then, well, you add these two, you get N. Similarly, if you add these two, you get N. Okay, this is an example of what a 2x2 contingency table would look like. With a contingency table, we often ask, is there a relationship between row and column variables? So we will learn a chi-square test. Chi-square test is an asymptotic test. In fact, we've already discussed the chi-square test, but I will discuss it when we are looking particularly at a contingency table, and we will learn Fisher's exact test, which is, as the name would indicate, an exact test. Here, really in both cases, the null hypothesis is that the 2 factors, and by that I mean row and column variables, are independent. The alternative, well, it's that the 2 factors are not independent. Now, let Pij denote the probability that an observation lands in row I, column J. Here we're dealing with a 2x2 contingency table, so I and J can both be 1. or 2. We can fill this in. This probabilities, we would have P11, row 1, column 2, row 2, column 1, and then row 2, column 2, like this. Under H0, Pij would be a product of the marginal probabilities. So let's write the marginal probabilities here. We could add across the row. We would have P11 plus P12. We could add across this row, P21 plus P22. Then we add down over this column, P11 plus P21. Finally, we add over the second column, P12 plus P22. Under H0, here is where we have each Pij written as a product of the marginals. For example, P11 is this times this. That's the first line. P12 here would be this times this. That is the second line. P21 would be this times this. That's the third line. Finally, P22, this probability times this probability. This kind of independence discussion came up much earlier in the semester when we discussed multivariate random variables and distributions. Okay, so we estimate the marginal probabilities from the random sample. For example, let me just paste. Here was one of our marginal probabilities. We estimate that from the random sample. So here we would take this number divided by n. So this would be capital R1 over n. I won't write them all out. Maybe I'll just write a few. So for example, let's do another one. For instance, here, copy. If we wanted to estimate this marginal probability, well, we take C1 over n. This would be like this, C1 divided by n. So that's just 2 examples, but we have 1, 2, 3, 4 marginal probabilities, and they would all be estimated in a similar fashion. Under H0, we have the following expected frequencies. So you notice here's the observed is OIJ, expected is EIJ. Well, we would take the probability times capital N, and the probability under H0 is just a product, would be capital Ri over n times capital Cj over n. These were our sample estimates of the marginal probabilities. So the chi-square test statistic, well, it looks very much like the chi-square test statistic from a few pages ago. We take observed minus expected squared, and then we normalize by expected. Here we add up over all the cells, and it looks exactly like this. Here, the degrees of freedom is 1. Generally, if you have a contingency table, you take the number of rows minus 1 times the number of columns minus 1. In R, we still use this, chi-sq.test. We have to format the table so that it understands it's working with a contingency table. I have this note to be careful here. A small p-value provides evidence for a relationship between the row and column variables. We would reject the null that the row and column variables are independent and conclude we have some sort of relationship. However, a small p-value does not give any information on the nature of the relationship. And so that's just care to take when you're making conclusions from the chi-square test. Now, I want to do an example by hand. This is made up, fictitious example, but it illustrates some things. So suppose we have the following contingency table. I have some disease, I have some gene, and the gene is either expressed or not. Patients either have the disease or not. And then I have the following counts. Well, let's put the totals here. We have 220. We have 550. adding over the rows, and then adding over the columns. 70 in total have gene G expressed, and 700 in total have gene G not expressed. Then this total in our random sample is here, 770. Now, I claim there is no relationship between the row and column variables. Why? Well, just staring at this, you see whether or not the patient has the disease. This gene seems to be not expressed in 10 times more people, right? If you take this column, it's 10 times this, and it doesn't really matter whether or not the patient has the disease. But let's put some of the statistics into this. So under H0, what is E11? Well, we know this is O11. Maybe I will write this. So this is O11. This is O row 2, column 1. This is O row 1, column 2, and O like this. Well, let's calculate this marginal probability, R1 over N. This is 220 divided by 770. I'll leave it as a fraction. This is 2 over 7. Okay, similarly, if you take C1 over N, this would be 70 divided by 770, 1 over 11. So the expected count, which would go here, well, we take 2 over 7. This is under H0 times 1 over 11 times 770. Well, what do we get? 770 divided by 77 is 10 times 2. We have 20. Well, you notice this is exactly O11. Moreover, if you went through each cell, you would be able to see that OIJ equals EIJ. And so if we go back to our statistic, you see the numerator for every cell is 0. So my Q is 0. This would give rel, the p-value is 1 here. The probability that a chi-square random variable is bigger than or equal to 0, that's 1. Just thinking about the chi-square distribution. There is no relationship between the row and column variables. This is kind of an extreme case, and as I mentioned, this was made up. It's unlikely you would see this exactly. Now, we are going to move into the Fisher's exact test, and before I do that, let me define a quantity based on this sample. It's called the sample odds ratio. What do you do here? Well, you take O11 times O22 divided by here, O12 times O21. So you take this divided by this. Okay, let's do it in this example. Well, we get 20 times 500 divided by 50 times 200, which is 1. Fisher's exact test. This is needed when there are small expected counts in some cells. This is because the chi-square test is an asymptotic test. Now, we begin with a definition of the population odds ratio. So if you think about the probabilities, the Pij that we discussed, they would be laid out like this. We would take P11 times P22 divided by P12 times P21. Independence is equivalent to the population odds ratio equaling 1. We saw that for sample odds ratio here in this most perfect independence case. The sample odds ratio was 1. Really motivated the definition and this equivalence here. Values farther from 1 represent a stronger association. So in Fisher's exact test, It uses the population odds ratio to test for independence. The null here is that the population odds ratio equals 1. And then, well, at least in the two-sided case, the alternative would be that the population odds ratio is not equal to 1. The test statistic is the sample odds ratio. Okay, Fisher's test. It considers all possible contingency tables that result in the same marginal frequencies. The p-value in Fisher's test is then a sum of certain hypergeometric probabilities. The sum is over contingency tables at least as extreme as the one that we have from our sample. And the idea is that Fisher's test answers the question, how extreme is this table? Now, in this remark, Fisher's test considers all possible contingency tables that result in the same marginal frequencies. It is a note that Fisher's test is a permutation test. The calculations in Fisher's test, because it is a permutation test, can be quite lengthy. The beautiful thing is, though, however, we have this Fisher.test in R. This is all I'm going to say about Module 8, Lesson 3. We had a lot of information here. I thank you so much.